Hello everyone. Today I'm going to introduce uh, an example to show how to parallelize CPU intensive computation with the Java 8 parallel string. So first I'm going to show an example of the sequential version and to compute the value of pi. Then I will parallel it using future and executable service. Finally, we're going to use the parallel string to implement that. Let's just start now. Um, so how the pi is computed? There's a famous formula basically. Pi divided by 4 is the sum of the sequence here. And for the sequence, each sequence, we can um, we can see it's basically defined by this formula. So if you use 1 to insert into this formula, you see the first item is the sign of the item here. So 1 minus 1 is 0. So minus 1 to the power of 0 is 1. So the sign is positive here. And for the second part of the formula, uh, so this is 2 multiplied by 1 minus 1, basically it's 1. So this is 1. For the second item, you see it's actually add another multiplication of minus 1. So this is a negative, and this two this basic odd number sequence basically 2 multiplied by 2 minus 1 is the 3, 1 divided by 3, so forth and so forth. So this formula is correct. So let's just trying to calculate the sequential version. Calculate pi sequential. So we input a parameter n, which is the number of items in the sequence. So the sum, the value is the sum of all these float numbers. So let's just do that. So because we start with 1 and end with n and I plus plus using this for loop. Okay, so in order to calculate the sign, let's just use this sign. The sign is initially positive, then the second is just flip and flop. So we can use this checked without using the function of power, which may be more expensive basically. So the next time the sign will be flipped, and this is 1 divided by 2 multiplied by I and minus 1. Alright, let's just return the sum and pi sequential. What's the value here? Calculate the pi sequential. Let's see. Oh, I forgot to multiply by 4 here because there's a 4 here. So just need to multiply by 4. Great, this looks correct now. Now let's parallel it. So the idea of parallelization is we divide the very long sequence to the number of uh, independent intervals. Then we calculate the sum of each interval using independent thread. Then we sum the sum together back. So the first parallelization we're going to try is using future and task. But regardless, we need to calculate the sequence in the interval with lower bound, let's just say m, and upper bound n. So it should be very similar to the first one, except the lower bound needs to be changed here. And also the initial value of the sign is no longer 1. It should be that interval, that formula. Basically, it's power -1 to the. So that's it. So now let's just write a parallel version. Apply parallel future. So the first thing we need to do is compute the length of the interval, which is the total number of the sequence and the parallel level, basically divided by parallel level. Then for the lower bound, we're going to have the lower bound for each interval using this for loop. So it will start with 0, the parallel level. Good. Now the lower bound is basically n is I multiplied by the interval length, because the first item is 1, not 0, so we have to add 1 here. Now let's create executable service. Service. So here, using executor, new fixed thread pool. The parallel level is just parallel. Alright, after we have this, we can submit each task now. The task is the future service. Calculate pi interval. This is the lower bound, low bound plus the length. So what's wrong with here? Oh yes, the sum should be a double. Great. Now we need to store all these futures into array list, then wait for all the futures to be completed. I think I need to import future here. Tasks, add, P. Okay, finally we just need to wait for the all filters to be done. And sum the result of them. Oh, interesting. Cannot recognize future. Unhandled exception. Let's just trying to catch the exception here. Try catch. And after the executor is the parallelization is done, we need to shut down the service. Great. So this is done. Let's just do compare whether parallel with future. Let's use something like 2 first. Okay, so you see the result are pretty much the same. So that's great. Now let's match the time. Uh, we need to do for the parallelization 1 as well. Let's then make it slightly easy to extract that variable. N is, let's make it a large number. So we'll see the difference of the time. Parallel level is 4. Alright, so you see the parallel program actually is slower. I believe this is because of the context switch. Let's add 2. Okay, so now you see the parallel version actually is faster than the sequential version. We can run multiple times, verify. Yes, it always is. The parallel version is fine, but let's see whether the parallel stream can doing a little bit better. With stream, parallel stream. So the structure of the program should be very similar. We still need to divide everything to multiple interval. So the interval length should be here. But we don't have the execute service, and instead of store the futures of the tasks, we store the lower bound. Lower bound. Now let's just try to find out the lower bound using a loop. And this shouldn't be here. Uh, this is the magic. Basically, we convert the collection to a string, and we map each item of the string uh, to using the function we define here, which is calculate the interval, pi interval. This is the lower bound, this is the upper bound, which is lower bound plus the length. And finally, we need to get the sum of them. Okay, but first we need to unboxing them using map to double. Then we call the sum. Great. So this is the sequential version, but we can see the parallel version is very similar after we test whether the results are correct. Now we have the before and after parallel with string. Alright, the sequential stream version has around the same running time of the for loop, which is very impressive because the code here is slightly is using high order function, all these things. So pretty much there's no overhead in Java implementation. Now let's just make it a parallel. Just change the stream to parallel stream. Let's test it. Wow, just by changing one line, we change a uh, sequential program to a parallel program, and we gain the speed. So compare with the version using the future, we can see the parallel string version is shorter. It's around 10 lines of code. Here it is around 50 lines, 20 lines of code. So it's a very large significant improvement, and the code here is more readable. Basically, we divide by the interval, we map each item from the stream using a function, then just reduce it using sum. Thank you to watch this video. If you enjoyed it, do you mind to subscribe it? Thank you. Bye bye.